This is chapter 5, and we're jumping now to section 4 here on power. So what we're going to do today is we are going to relate concepts of energy, time, and power, calculate power in two different ways, and explain the effect that machines have on work and power. So what is power? Power is the rate at which work is done. So remember, we've talked about this word rate before, and rate is a word that is connected to time. So another way to say this is power is how fast work is done. So let's pause here and look at an example to think about what power means. So we have two people here, and they're both climbing a rope, okay? And they both have the same mass. And they're going to climb the rope the same distance, 3 meters each. But one person A here can climb it in 10 seconds, and the other person needs 30 seconds to climb it. So it's tempting to think that because person A here climbs it faster that he must do more work. But let's check and see. So if we calculate the work equals force times distance. And we have mass here, so we need to include that. So the work will be against their own force of gravity. So it'll be mass times gravity times distance. And if I plug all those numbers in for person A, I have 65 times 9.8 times 3 meters. And plugging all that in, you have 1,913 joules of work. If now I do it for person B, okay, and I'm going to do his in pink now, the work of person B will also be force times distance, and it's his force of gravity he's working against, so it will be M times G times D also. And again, mass is the same, it's 65 kilograms, he climbs 3 meters, gravity doesn't change, so when we calculate that all out, we also get 1,913 joules. So the work that these men both do is the same. So work does not change even though their speeds are different. What changes now is power. So power, our equation for power is work divided by the change in time. So now if we take each of these, okay, and say that the power of A is work A divided by time, we find that work A here, the 1913, divided by 10 seconds is 191 watts. If we take power of person B, then we have work B divided by time. And his work is 30 seconds. So 1,913 divided by 30 ends up being 63.7 watts. So they both do the same amount of work. They both have 1,913 joules, but their power is what's different. Because the one person does it faster, so he has to use more power than the person who does it slower. So I just used the units of power, but let's take a look at it more. So power is work divided by time, as you saw from the last example that we did. Now if we take that and we plug in our units that we know that joule is the unit of work and seconds is the unit of time. And what that is we have a new derived unit called the watt. Now it can be a little confusing sometimes because it's a capital W, and when we write the unit, like in our example, we have 67 watts, we use a W. So you have to remember that what you calculated was power, and this is watts, even though we had this big capital W in here that is also watts. So make sure you keep track of what you're doing. So we're going to take a little bit to look at the equation, okay, because we know that work equals force times distance. So we can take that and plug that into our equation for power, and we end up with force times distance divided by a change in time. Now if we look at this and rearrange it a little bit, we could write it like this. Okay? And right now we've been using d for distance, but we also used to write it as delta x. So if you think of it as delta x divided by delta t, that's a thing we already know. It's velocity. So it turns out that power is also equal to force times velocity. And we can use that equation as well, and we will still get the same unit of watts and the same answers as if we use work divided by time. So let's do an example now. So in this example here, it asks, how long does it take a 19 kilowatt steam engine to do 6.8 times 10 to the 7 joules of work? So what we know is that the power is 19 kilowatts, which we can rewrite as 19,000 watts. We know the work, and we're asked to find the time. So we can plug in our equation, and we have power, work, and change in time. So we can use the equation as we originally saw it the first time here. We can solve for delta t, since that's what we want. So delta t will be equal to work divided by power. Then if we plug in our numbers, we'll have 6.8 times 10 to the 7th joules divided by our 19,000 watts. And we get an answer of 3,578.9 seconds. Okay. And if we wanted to make that just make a little bit more sense, I converted it to minutes already, and it's 59.6 minutes. So just about an hour it would take. We're going to do one more example because we have the equation in a couple different forms now. So this time we have a 50 kilogram student climbs 5 meters up a rope at a constant speed. If the student's power output is 200 watts, how long does it take the student to climb the rope? How much work does the student do? So what we need to look at here is we know all these different things. We know mass, we know the distance, we know the power, we don't know time, and we don't know work. And that's what they're asking us to find. So we have the equation, okay, and I wrote it out like this because it shows all the different forms at once, except I could add equals FV. But if we look at this, okay, we don't have velocity in here, and we don't know time, so there's no way that we're going to use the FV form for this time. Okay, and in fact, again, we've got force here, right? But all we have is mass. So again, we're going to have to use F equals mass times acceleration of gravity in order to find everything here. So we want to find time. We know mass, we know acceleration of gravity, we know distance. So let's go ahead and plug this in with power to find the answer. So the power is 200 watts, and that's going to be equal to our F equals ma version of force. So we'll have 50 kilograms times 9.81, and then times our distance of 5 meters. And we're going to divide that by time. And now if we solve all of that, I'm going to run out of room if I do it, but I did it before, we find that the time comes out to 12.26 seconds. So there is our first answer. The second part then asked us to find work, which in reality we already did because we know that work equals force times distance. So really that's going to be just this part of the equation here because we had mass times acceleration times the distance. So if I plug all that in, just that part, work equals force times distance, which happens to equal this part here I've circled. And when we calculate that out by itself, it ends up being 2,452.5 joules. So there is our work. So let me know if you have any questions in class, and I'll see you guys there.